Everything you see in the night sky is a tiny fraction of reality. We are about to journey through 25 mind-blowing facts that will fundamentally warp your understanding of the cosmos. By the end, you will see the universe not as a static stage, but as a dynamic, bizarre, and deeply interconnected mystery. We will confront invisible forces that shape galaxies, visit places where time itself bends, and uncover secrets that sound like pure fiction. How many of your basic assumptions about space and time are about to be shattered? Our entire reality, everything we know and can touch, is just a cosmic afterthought. If you could gather all the matter that makes up every star, every planet, every galaxy, and every single human being who has ever lived, you would have collected less than 5% of the universe. The rest, the overwhelming majority of everything that exists, is utterly invisible to us. We call these mysterious components dark matter and dark energy, and they are the true architects of our cosmos. Dark matter, making up roughly 27% of the universe, is the universe's hidden skeleton. We know it exists not because we can see it, but because of its immense gravitational pull. Picture a spinning galaxy. The stars on its outer edges should be flung out into space, moving too fast for the galaxy's visible mass to hold them in. Yet they stay in orbit as if held by the grip of something massive and unseen. That something is dark matter, an invisible web that holds galaxies together and dictates how they form and move. Then there is dark energy, the most baffling force of all. It comprises a staggering 68% of the universe, and it does the opposite of gravity. Instead of pulling things together, it pushes space itself apart, causing the expansion of the universe to accelerate. This force is so dominant that it will ultimately decide the fate of everything. We can see its fingerprint in the faint afterglow of the Big Bang, the cosmic microwave background, a snapshot of the infant universe that reveals the seeds of all structure. So, the universe we gaze upon is merely the glittering decoration on a framework we cannot see, driven by a force we do not understand. This means we are essentially blind to 95% of our own reality. What other fundamental truths are hiding just beyond our perception? If the hidden framework of the universe feels abstract, consider a world where the most basic rhythm of existence is turned upside down. On Venus, a single day lasts longer than an entire year. This is not a metaphor or an exaggeration. For the sun to rise, travel across the sky, and set on Venus requires 243 Earth days. That is how long it takes the planet to complete one full rotation on its axis. Yet, in that same span of time, Venus has already completed its entire journey around the Sun, and then some, because its orbital year is only 225 Earth days. You could celebrate 2 birthdays there before you witnessed a single sunrise. This bizarre reality is compounded by another strange fact. Venus spins in the opposite direction to almost every other planet in our solar system. From its perspective, the sun would rise in the west and set in the east. Why would a planet behave this way? The leading theory points to a cataclysmic event in the distant past, a collision with a massive object so powerful it literally stopped the planet in its tracks and sent it spinning backwards like hitting a spinning top with a hammer. This slow, reversed rotation contributes to an environment of pure extremity. The surface of Venus is a vision of hell, shrouded under thick, toxic clouds of sulfuric acid. The atmospheric pressure is 92 times greater than Earth's, equivalent to being nearly 1 kilometer deep in our ocean, and the temperature is a constant 870 degrees Fahrenheit, hot enough to melt lead. This combination of a day outlasting a year and a surface that defies survival makes Venus not just another planet, but a stark reminder that the rules we take for granted are not universal laws. They are local customs, and the cosmos is full of exceptions. Venus shows us how alien a single world can be, but the strangeness does not stop at the edge of our solar system. It is woven into the very fabric of the cosmos on a scale that is almost impossible to comprehend. Scattered across the faint, ancient light of the cosmic microwave background, the afterglow of creation itself, astronomers have found a blemish. It is called the cold spot, and it is not just a little cooler than its surroundings. It is a colossal region of space in the constellation Eridanus, roughly 1.8 billion light-years across, that is profoundly cold and eerily empty. To grasp that size, if you could travel at the speed of light, it would take you nearly 2 billion years just to cross from one side to the other. Within this staggering volume, there are far fewer galaxies and clusters than there should be. It is a cosmic desert of unimaginable proportions, a supervoid, but its emptiness is not what makes it a profound mystery. The real puzzle is the cold. The cosmic microwave background radiation, which is remarkably uniform across the sky, is significantly cooler in this region. According to our standard models of cosmology, such a large and deep cold spot is extraordinarily unlikely to have formed by random chance. It is as if you baked a perfectly smooth loaf of bread and found one massive, icy hole inside. So what could have caused it? One leading and mind-bending theory suggests this void is not just empty. It could be a bruise, a scar left from a collision between our universe and another bubble universe in the vast multiverse. The energy of that collision, the theory goes, could have drained away, leaving this region colder and emptier than anywhere else. Another possibility points to exotic physics, perhaps a flaw in the very inflationary model that describes the universe's rapid expansion after the Big Bang. The cold spot remains an active area of research, a glaring anomaly on our map of the infant universe that refuses to be explained away. It is a reminder that our most successful theories are still incomplete, and that the cosmos may hold echoes of events from beyond our own reality. What other imprints from other realms might be hidden in the light? The cold spot is a cosmic ghost, a hint of something beyond our universe. But to find a place where the rules of reality truly break down, you need to look at the most extreme objects in existence. Near a black hole, time itself begins to slow to a crawl. This is not science fiction. It is a direct prediction of Albert Einstein's theory of general relativity, which tells us that gravity is not just a force pulling on objects. It is a curvature, a warping of the very fabric of space and time. The stronger the gravity, the more space-time is bent and the slower time flows. Imagine space-time as a vast, flexible trampoline. Place a bowling ball in the center and it creates a deep well. A marble rolled near the edge will follow a gentle curve, but if you roll it close to the bowling ball, it will spiral inward rapidly. Now think of time as the ticking of a clock placed on that trampoline. A clock far out on the flat edge ticks at a normal rate, but a clock placed deep in the well near the heavy bowling ball will tick much more slowly from the perspective of the distant observer. A black hole is the ultimate bowling ball, a point of such immense density that it creates a gravitational well so deep not even light can escape. If you could somehow hover just outside its point of no return, the event horizon, your experience of time would be almost normal. But to anyone watching you from a safe distance, your movements would appear to slow down, your signals would stretch out, and you would seem to freeze in place, fading to red and then vanishing from view as you crossed the threshold. This effect was powerfully dramatized in the film Interstellar, where astronauts visiting a planet orbiting a supermassive black hole experience only a few hours, while their colleague waiting in orbit ages decades. The science behind that scene is very real. We even account for a much milder version of this effect here on Earth. The atomic clocks on GPS satellites in orbit, experiencing slightly weaker gravity, tick faster than identical clocks on the ground. If engineers did not constantly correct for this relativistic time drift, your phone's navigation would be off by several miles within a single day. So, gravity does not just pull on matter. It pulls on time, stretching and warping the one-way flow we consider constant. This means the universe has no single, universal clock. Your experience of time is literally shaped by where you are and what gravity you feel. If time is this malleable, what other fundamental truths might be just a matter of perspective? That malleable nature of time has a direct and measurable consequence right here in our celestial neighborhood. Our own moon is in a slow but steady retreat. Each year, it moves about 3.8 centimeters farther away from Earth. That is roughly the same rate your fingernails grow. This tiny annual drift is the result of a gravitational tug-of-war and a transfer of energy between Earth and its satellite. The moon's gravity pulls on our oceans, creating the bulges we know as tides. But Earth is spinning rapidly, and this rotation drags those tidal bulges slightly ahead of the direct line between Earth and the moon. Those forward-shifted bulges, in turn, exert their own gravitational pull on the moon. This gentle, constant tug gives the moon a tiny boost of energy, pushing it into a slightly higher orbit. In exchange, Earth loses a corresponding amount of rotational energy. Our planet's spin is very gradually slowing down, making our days longer by about 1.7 milliseconds every century. It is an imperceptible change now, but over cosmic timescales it compounds dramatically. Billions of years ago, a day on Earth was only about 5 hours long, and the moon loomed much larger and closer in the sky. In the far future, the dance will continue to evolve. Earth's rotation will continue to slow until it becomes tidally locked with the moon, much like the moon is already locked with us, showing only one face. At that distant point, a single Earth day will last as long as a lunar month, about 47 of our current days, and the moon will hang motionless over one hemisphere of the planet, forever hidden from the other. This also means the spectacle of a perfect total solar eclipse, where the moon can just barely cover the sun's disk, is a temporary gift of our current epoch. As the moon recedes, its apparent size in our sky will shrink. In roughly 600 million years, it will be too small to completely obscure the sun, and total solar eclipses will vanish from Earth's experience forever. This slow celestial drift reminds us that even the most familiar fixtures of our sky are in a state of constant, graceful flux, writing a story that unfolds over timescales far beyond human history. While the moon's retreat is a slow and graceful ballet, the death of a star can forge something of unimaginable violence and density. When a massive star explodes in a supernova, its outer layers are blasted into space, but its core collapses under its own immense gravity. If that core is between about 1.4 and 3 times the mass of our Sun, it does not become a black hole. Instead, it crushes down into one of the most extreme objects in the universe, a neutron star. To understand its density, picture a single sugar cube. Now imagine compressing the entire mass of Mount Everest into that tiny space. That is still not enough. A sugar cube-sized piece of a neutron star would weigh about 1 billion tons here on Earth. A teaspoonful would outweigh every single human being on the planet combined. This insane density comes from what happens to matter under such catastrophic pressure. The intense gravity overwhelms the forces that normally keep atoms apart. Electrons are smashed into protons and they merge to form neutrons. The entire star, often only about 12 miles across, becomes a colossal atomic nucleus, a city-sized ball of neutrons packed together with almost no empty space. Its structure is layered like a cosmic onion. The surface is a crust of iron nuclei locked in a crystalline lattice. Beneath that, the pressure is so great that the neutrons flow without any friction at all, a bizarre state called a neutron superfluid. And at the very heart, physicists theorize the conditions might be so extreme that the neutrons themselves break down into their constituent parts, creating a soup of free quarks and gluons, the fundamental building blocks of all matter. But the strangeness does not stop there. Neutron stars often spin at dizzying speeds, rotating hundreds of times per second. This rapid spin, combined with beams of intense radiation shooting from their magnetic poles, creates a lighthouse effect. If those beams sweep across Earth, we detect them as perfectly regular pulses of radio waves, and we call the object a pulsar. Their magnetic fields are another realm of extremity, up to a quadrillion times stronger than Earth's field, a force so powerful it could strip the information from every credit card on our planet from halfway across the solar system. These cosmic diamonds are not just stellar corpses. They are natural laboratories for physics under conditions we could never hope to recreate, testing the very limits of what matter can become. The sheer density of a neutron star warps space and time around it, but there is an even larger force at work, one that pulls on our entire galaxy. We are not floating freely through the cosmos. The Milky Way, along with thousands of other galaxies, is being pulled toward a mysterious point in the constellation Centaurus at an astonishing speed of over 1 million miles per hour. This cosmic destination is known as the Great Attractor, a gravitational anomaly so powerful it defies our understanding of the universe's large-scale structure. For decades, this region was a profound puzzle. Our telescopes could not see it directly because it lies in a direction obscured by the thick band of dust, gas, and stars at the heart of our own galaxy. Astronomers call this our blind spot, the zone of avoidance. It is like trying to see a distant city through a dense, permanent fog. We knew something massive was there only by its gravitational pull, watching how entire galaxies were streaming toward it like leaves caught in a vast, invisible river. As observation technology improved, particularly with infrared and radio telescopes that can peer through the cosmic dust, we began to map this hidden realm. What we found was not a single, unimaginably dense object, but an immense concentration of mass, a massive cluster of galaxies known as the Norma cluster. This cluster, along with our own local group of galaxies, the Virgo cluster, and many others, are all part of a single, staggering structure. We now understand the Great Attractor not as an ultimate destination, but as the core gravitational anchor of something far grander, the Laniakea supercluster. Laniakea is a Hawaiian word meaning immense heaven, and it is a fitting name. This supercluster is a web of 100,000 galaxies spanning over 500 million light-years. Within this vast cosmic continent, all galaxies are flowing along filaments of dark matter toward the same gravitational basin, the Great Attractor, so our galactic journey is not a lonely one. We are part of a colossal migration, one of countless galaxies surfing the gravitational currents of the universe toward a common point, all orchestrated by the hidden hand of dark matter. This reveals a universe not of random scatter, but of immense flowing architecture. If our local supercluster is being pulled, what else is moving in the cosmic dark? The gravitational currents of Laniakea reveal a cosmos of immense structure, but some theories suggest the architecture of reality could be even more profoundly symmetrical. There is a wild, speculative idea in physics that our universe has a perfect mirror image, a twin born at the same instant where time itself flows backwards. This is the concept of the anti-universe, and it emerges not from science fiction, but from a deep desire to explain two of the most stubborn puzzles in modern cosmology, dark matter and the strange nature of neutrinos. The proposal hinges on a fundamental symmetry in physics known as CPT symmetry. CPT stands for charge, parity, and time. It means that if you take any physical process and simultaneously reverse the charge of every particle, flip it in a mirror, and run it backwards in time, the laws of physics should still hold true. Our universe, as we observe it, respects this symmetry in its laws, but not perfectly in its initial conditions. The Big Bang seems to have been a moment of profound asymmetry, creating a universe filled with matter but almost no antimatter. The anti-universe theory asks a radical question: what if the Big Bang was perfectly symmetric after all? In this view, the moment of creation did not produce just one universe expanding forward in time. It produced two. Our universe expanding forward from that point is made of matter and experiences time as we know it. The other universe, inextricably linked to ours, is its CPT mirror. It would be made of antimatter, be mirror reflected, and crucially, expand backwards in time from the Big Bang. From our perspective, looking toward the moment of creation, we would see time in that other universe running in reverse. This solves puzzles with elegance. The mysterious dark matter that holds galaxies together could simply be a new type of neutrino that exists in our universe because of its connection to this mirror realm. The theory naturally accounts for the observed abundance of dark matter without needing to invent entirely new, undetected particles. It also explains why neutrinos are so bafflingly light compared to other particles, a long-standing mystery. Now, it is crucial to emphasize this is a highly theoretical model, a beautiful piece of mathematics on paper. We cannot see or interact with this anti-universe directly because it exists on the other side of the Big Bang, a barrier we cannot cross. Any signal from it would be lost in the primordial fireball of creation. Yet, the very fact that such an idea is taken seriously by physicists shows how far we must stretch our imaginations to comprehend the cosmos. It suggests that our arrow of time, our relentless march from past to future, might not be a universal absolute. It could be a local phenomenon with an equal and opposite flow existing just on the other side of the beginning of everything. If time can run backwards in a mirror cosmos, what other fundamental aspects of our reality might be doubled, reflected, or inverted in ways we cannot yet perceive? The idea of a mirrored cosmos challenges our deepest assumptions, but even within our own universe, the void is an illusion. Space is not a perfect, empty vacuum. Between the stars, in what we perceive as utter blackness, there exists a diffuse and ghostly sea of matter known as the interstellar medium. In most regions, this medium is so thin it would qualify as an ultra-high vacuum in any laboratory on Earth, containing only about 1 atom per cubic centimeter. To visualize that emptiness, imagine taking a single breath of air and spreading all the molecules from that breath evenly throughout the entire volume of a typical house. That is the profound tenuity of deep space, yet this near-nothingness is the raw material of creation. It is composed mostly of hydrogen and helium gas, the primordial elements forged in the Big Bang, along with microscopic grains of cosmic dust made of heavier elements like carbon and silicon. These dust grains are incredibly small, finer than particles of smoke, but in vast clouds they can block the light from distant stars, creating the dark patches we see in the Milky Way. Coursing through this thin soup are cosmic rays, which are not rays at all but atomic nuclei, mostly protons, accelerated to nearly the speed of light by supernova explosions and other violent events. They constantly rain down on our planet, passing through our bodies unnoticed, a silent reminder of the dynamic activity hidden in the void. It is from this sparse interstellar medium that new stars are born. Gravity can slowly pull together a vast, cold cloud of this gas and dust over millions of years. As the cloud contracts, it fragments into dense clumps that heat up under their own weight until nuclear fusion ignites in their cores, lighting new suns. When a young, hot star switches on, its intense radiation can illuminate the surrounding cloud from within, sculpting and energizing the gas to glow in spectacular reds and blues. We see these illuminated clouds as nebulae, the stunning stellar nurseries and graves that adorn telescope images. So, the emptiness of space is a fertile emptiness. The grand spiral arms of galaxies are not just collections of stars. They are dynamic ecosystems where this tenuous medium cycles through phases of dispersal, collapse, and rebirth. The next time you look at the dark sky, remember you are gazing not into a void, but into a diffuse ocean, the primordial soup from which every star, planet, and ultimately every one of us was formed. That diffuse ocean of interstellar gas is just a single thread in a tapestry of staggering scale. Zoom out far enough, and the true architecture of the cosmos reveals itself. The universe is not a random scattering of galaxies like stars tossed across black velvet. Instead, it is structured as a colossal cosmic web, a vast, intricate network of brilliant filaments, dense clusters, and immense dark voids. This is the largest known structure in existence, a framework woven from gravity and dark matter that stretches across the observable universe. Picture a three-dimensional spiderweb, but one where the silken threads are chains of thousands of galaxies, and the empty spaces between them are voids so enormous they could swallow entire superclusters. Our Milky Way resides on a filament within the Laniakea supercluster, a single neighborhood in this boundless cosmic city. The scale of this web defies easy comprehension. The filaments themselves can be hundreds of millions of light-years long, while the voids between them, often spherical in shape, can span hundreds of millions of light-years across, containing almost no galaxies at all. This structure emerged from tiny quantum fluctuations in the dense, hot soup of the infant universe, magnified by inflation and then sculpted over billions of years by the relentless pull of gravity. Dark matter acted as the invisible skeleton, its gravitational wells attracting the normal baryonic matter. Gas flowed along these dark matter filaments, cooling and collapsing to form galaxies at the intersections, like glitter accumulating at the knots of a net. One of the most stunning examples of this filamentary structure pushes our understanding of the universe to its limits. It is called the Hercules Corona Borealis Great Wall. Discovered by mapping gamma-ray bursts, the brilliant flashes from the depths of massive stars, this structure is a galaxy filament estimated to be over 10 billion light-years in length. To grasp that, a beam of light, the fastest thing in the universe, would need 10 billion years to travel from one end to the other. This presents a profound cosmological problem. According to a fundamental principle called the cosmological principle, the universe on very large scales should look roughly the same in every direction. Matter should be distributed with a degree of homogeneity. The existence of a structure as vast as the Hercules Corona Borealis Great Wall challenges that assumption. It is so large it seems to violate models of how structure could have formed within the age of the universe. Is it a true connected filament or a chance alignment of smaller clusters seen in projection? The debate continues, but its very discovery forces us to question the limits of our maps and the true scale of cosmic architecture. Three-dimensional visualizations of this web, built from galaxy surveys like the Sloan Digital Sky Survey, are among the most beautiful and humbling images in all of science. They show a universe of breathtaking order and connectivity, a luminous neural network on a scale that dwarfs all human imagination. We are not just living in a galaxy. We are embedded in a single knot of light within a web whose full extent we may never fully see. That cosmic web of galaxies is the grandest structure we know, but its true purpose may be deeply personal. The immense filaments and stellar nurseries exist for a single, profound reason: to forge the very ingredients of life. Every atom in your body, from the calcium in your bones to the iron in your blood, was created in the heart of a star that died long before our sun was born. You are literally made of stardust. This is not poetry, it is the hard physics of nucleosynthesis. In the first few minutes after the Big Bang, the universe was a searing hot soup of particles that cooled and fused into only the lightest elements: hydrogen, helium, and a trace of lithium. That was it. For hundreds of millions of years, the cosmos contained nothing heavier. The universe could not make planets or oceans or life from hydrogen and helium alone. The recipe for everything else required the intense pressure and heat found only in the cores of stars. Inside a star like our Sun, hydrogen atoms fuse into helium, releasing the energy that makes it shine. But in more massive stars, the story continues. As the star ages and its core runs out of hydrogen, it begins to fuse helium into carbon. Then, under even greater pressure, carbon fuses into oxygen, and so on, climbing the periodic table in a desperate struggle against gravity. In a step-by-step stellar alchemy, the star forges neon, magnesium, silicon, and finally iron. Creating iron is a star's death sentence. Fusing iron does not release energy, it consumes it. With its energy source cut off, the star's core collapses in a fraction of a second, then rebounds in a cataclysmic supernova explosion. This final, violent act is the universe's ultimate forge. The incredible energy of the blast creates elements heavier than iron, like gold, silver, and uranium, and then scatters the entire enriched inventory of the dead star, carbon, oxygen, nitrogen, iron, everything, out into the interstellar medium. Even gentler stars like our Sun will contribute. In their final stages, they puff off their outer layers in beautiful planetary nebulae, seeding space with carbon and other life-essential elements. This scattered stardust, mixed with the primordial hydrogen and helium, then coalesces into new generations of stars, planets, and eventually us. So when you look up at the night sky, you are not a separate observer gazing at distant points of light. You are the universe looking back at itself. The oxygen you breathe, the carbon that forms the backbone of your DNA, the iron that carries oxygen in your bloodstream, all were forged in stellar furnaces and delivered across space and time by stellar explosions. We are not just in the universe is in us. This cosmic recycling connects every person to the most epic story imaginable, a narrative written in atoms across billions of years. That stardust within you is still bathed in the faint, ancient warmth of creation itself. The universe has a temperature, a baseline chill that permeates every cubic centimeter of space. It is not absolute zero. Instead, the void glows with a whisper of heat, a uniform radiation of about 2.7 Kelvin, which is minus 455 degrees Fahrenheit. This is the cosmic microwave background, and it is the oldest light we can possibly see. To understand its origin, we must travel back to the universe's infancy. For the first 380,000 years after the Big Bang, the cosmos was an opaque, searing hot plasma, a dense fog of particles and light where photons could not travel freely. They were constantly scattered by free electrons like headlights in a thick, blinding fog. But as the universe expanded and cooled, a pivotal moment occurred, one physicists call recombination. Electrons combined with protons to form the first stable hydrogen atoms. Suddenly, the fog cleared. The universe became transparent. Those photons, which had been trapped in the hot plasma, were finally set free to travel across space. We detect that first flash of liberated light today, stretched and cooled by 13.8 billion years of cosmic expansion. The visible light from that primeval flash has been redshifted all the way down into the microwave part of the spectrum, hence the name. This radiation is not coming from any one point in the sky. It fills the entire universe, arriving at Earth from every direction with near-perfect uniformity. It is the afterglow of the Big Bang, and if you could see microwaves, the entire sky would glow with a soft, uniform light. But the story gets even more profound. When scientists first mapped this background with exquisite precision using satellites, they discovered it is not perfectly smooth. There are tiny, tiny variations in temperature, anisotropies, on the order of 1 part in 100,000. These minute fluctuations, these hot and cold spots, are the cosmic seeds of everything. They represent regions of slightly higher and lower density in that early, transparent universe. Over billions of years, gravity acted on those seeds. The slightly denser, warmer spots pulled in more matter, growing into the vast cosmic web of galaxies, clusters, and filaments we see today. The cooler, less dense spots evolved into the great cosmic voids. So, the cosmic microwave background is far more than a relic. It is a baby picture of the cosmos, a detailed snapshot of the universe at 380,000 years old. And imprinted in its subtle temperature patterns is the blueprint for all of cosmic history, the gravitational recipe for stars, galaxies, and ultimately for us. This means the largest structures in existence can trace their lineage back to the faintest whispers in the cold of space. The blueprint for cosmic structure is written in that ancient light, but closer to home, our own solar system may still hold a major secret. Astronomers are hunting for a ghost world, a hypothetical giant they call Planet 9. This is not a crackpot theory. It is a serious scientific hypothesis born from a persistent anomaly in the orbits of the most distant objects in our solar system. Far beyond Neptune, in the frigid, dark realm of the Kuiper Belt, there exists a population of icy bodies known as trans-Neptunian objects. A handful of these, with orbits that take them hundreds of times farther from the Sun than Earth, behave strangely. Their elongated paths are clustered together in a way that defies random chance. They seem to be shepherded, their orbits aligned by the gravitational influence of something massive we have not yet seen. The mathematics are compelling. The simplest explanation for this peculiar orbital clustering is the presence of a planet. Not a small, rocky world, but a true giant, estimated to be between 5 and 10 times the mass of Earth. That would make it a mini ice giant, similar in composition to Uranus or Neptune. Its orbit would be highly elliptical and tilted, taking it on a monumental journey around the Sun that could last 10,000 to 20,000 years. At its closest approach, it might come within a few hundred astronomical units, but at its farthest, it could be over 1,000 times farther from the Sun than Earth. This extreme distance and its likely dark, cold surface are why we have not spotted it yet. It reflects virtually no sunlight, hiding in the profound blackness of the outer solar system. The hunt is on with some of the world's most powerful telescopes, like Subaru in Hawaii, which are meticulously scanning the predicted orbital path, looking for a single, faint point of light moving slowly against the background stars. Finding Planet 9 would be a monumental discovery, rewriting the story of our solar system's formation and dynamics. It would explain not just the clustered orbits, but other puzzles like the unusual tilt of the Sun's axis. Its discovery would remind us that even in our own cosmic backyard, there are still worlds of significant size waiting to be found, proving that exploration is far from over. Gravity's power to warp light is not just a theoretical curiosity. It is a tool that allows us to see the invisible. When a massive object like a galaxy cluster sits between us and a more distant galaxy, its immense gravity acts as a cosmic lens, bending and magnifying the light from that faraway object. This phenomenon is called gravitational lensing, a direct prediction of Einstein's general relativity, and it turns the universe into a natural telescope of staggering power. The effect works because gravity curves space-time itself. Light, traveling along this curved geometry, follows a bent path. From our perspective, it looks as if the light is being pulled toward the massive foreground object. The results can be breathtakingly beautiful and scientifically invaluable. In a perfect alignment where the distant light source is directly behind the massive lens, the light can be warped into a complete circle around the foreground cluster, a shimmering halo known as an Einstein ring. More often, the alignment is slightly off, creating multiple distorted images of the same background galaxy, stretched into long, faint arcs of light around the cluster's edges. These are not different galaxies, they are cosmic mirages, ghostly copies of a single object whose light has taken different paths around the gravitational well. This natural magnifying glass is one of astronomy's most powerful techniques. It allows us to see galaxies so distant and faint they would otherwise be utterly undetectable, even with our largest telescopes. By studying these magnified images, we can peer back into the universe's early chapters, observing the first generations of galaxies as they were forming. Gravitational lensing also provides the most direct method for mapping the distribution of dark matter. Since the lensing effect depends on total mass, both visible and dark, by measuring how severely the light is bent, astronomers can calculate how much dark matter is present in the foreground cluster and precisely where it is concentrated. It reveals the invisible skeleton of the cosmos in exquisite detail. So, the universe provides its own lenses, trapping and bending light in a gravitational bottle to show us wonders hidden in the deep dark. If gravity can magnify the distant past, what other cosmic illusions might be tricking our eyes right now? That ancient light from the cosmic microwave background has traveled for billions of years, but even the sunlight warming your face today is far older than it appears. The journey of a single photon of light from its birth within our sun to its arrival on Earth is an epic tale of patience and chaos. It begins in the solar core, a furnace of unimaginable pressure and temperature where hydrogen nuclei fuse into helium. This nuclear fusion releases energy in the form of gamma-ray photons, the most energetic form of light. That photon, born in a flash, does not simply zip out of the sun in a straight line. Instead, it immediately enters a dense prison, the radiative zone. This region is so packed with matter that the photon cannot travel more than a tiny distance before it collides with a charged particle, is absorbed, and then re-emitted in a random new direction. This process repeats itself over and over, trillions upon trillions of times. The photon is trapped in what physicists call a random walk, a staggeringly inefficient drunken stumble through an atomic maze. On average, it takes a photon 100,000 years to fight its way through this thicket, to travel from the core to the outer boundary of the radiative zone. To visualize this, imagine trying to walk across a crowded, chaotic dance floor where every step forward is met by someone pushing you sideways or backwards. Your progress to the other side would be agonizingly slow, even though the distance is short. That is the life of a photon in the sun's heart. Once it finally reaches the convective zone, the outer layer of the solar interior, the journey changes. Here, vast currents of hot plasma rise like bubbles in a boiling pot, carrying the photon upward much more efficiently. It rides these currents to the sun's visible surface, the photosphere, and finally, after its 100,000-year odyssey, it breaks free into the vacuum of space. From that point, the photon travels in a straight line at the speed of light, covering the 93 million miles to Earth in just over 8 minutes. So the sunlight that touches you is a blend of deep time and instantaneous travel. The energy you feel was created 100 millennia ago, during an era when our human ancestors were just beginning to spread across the globe, and it has been bouncing around inside a star ever since, waiting for this moment to escape and complete its final, swift sprint to your eyes. This means we see the sun not as it is now, but as it was over 8 minutes ago, and we feel its energy as it was crafted in an age lost to prehistory. The ancient energy within sunlight hints at a single star's immense lifetime, but our sun is just one member of a family whose size defies all earthly comparison. The number of stars in the observable universe is so vast it makes every beach on our planet seem empty. Astronomers estimate our own Milky Way galaxy contains roughly 100 billion stars. Now try to hold that number in your mind. 100 billion is a 1 followed by 11 zeros. It is an amount so large it becomes meaningless to our daily experience. But that is just our galactic neighborhood. When we point our most powerful telescopes at the darkest patches of sky, we find that the universe is filled with galaxies, each an island of billions of its own suns. The current best estimate suggests there are around 2 trillion galaxies in the observable universe. Multiply 100 billion stars per galaxy by 2 trillion galaxies, and you arrive at a number so colossal it is written as 10 to the 24th power. That is a 1 followed by 24 zeros. To give this scale some grounding, we often compare it to the number of grains of sand on all the beaches and deserts of Earth. That is a classic, humbling analogy. Geologists estimate our entire planet holds about 7.5 quintillion grains of sand, which is 7.5 times 10 to the 18th power. It is an almost inconceivable number, yet when you place it next to the estimated number of stars, the stars win by a factor of over 1 million. For every single grain of sand on Earth, there are over 1 million stars shining in the cosmos. Picture standing on a vast, endless beach scooping up a handful of sand. Within your palm, you hold a few thousand grains. The stars corresponding to just that handful would outnumber every person alive today. This staggering comparison does more than just convey scale. It fundamentally reshapes our place in the narrative. Each of those trillions upon trillions of stars is a sun, a potential anchor for planetary systems. While many may be solitary or host inhospitable worlds, the sheer statistics make it almost a certainty that our galaxy and the universe beyond is teeming with planets. The cosmos is not a sparse, dark void punctuated by the occasional light. It is a glittering, crowded metropolis of fire, a testament to nature's prodigious creativity. If the building blocks for life are as common as the stardust we are made from, then among those million stars for every grain of sand, how many worlds might hold their own stories, their own oceans, their own skies? Such staggering numbers of stars guarantee that many will meet a violent end, and the remnants they leave behind are places where the ordinary rules of matter cease to exist. The density of a neutron star is not just a curious statistic, it is a force of absolute annihilation. To bring a single teaspoon of that material to Earth would not be a scientific acquisition, it would be an extinction-level event. That tiny volume, no larger than a sugar cube, would weigh approximately 1 billion tons. It would possess the mass of Mount Everest compressed into a speck you could hold on a spoon. The moment it arrived in our planet's gravity, the consequences would be both instantaneous and apocalyptic. Freed from the immense gravitational field of the neutron star that holds it together, this ultra-dense matter would violently expand. But its more immediate effect would be gravitational. With the mass of a mountain concentrated in a pinprick, its own gravitational pull would be terrifyingly intense for its size. It would not simply sit on the ground. It would fall straight through the floor, the bedrock, and the planet itself, as if the Earth were made of smoke. The teaspoon would punch through the crust like a bullet through tissue paper, its immense density allowing it to plow through solid rock as if it were empty space. It would accelerate toward the Earth's core, carving a microscopic tunnel and displacing a massive volume of material in its wake. The friction, though minuscule, would generate immense heat, but the object's momentum would be unstoppable. It would oscillate, a hyper-dense pendulum, rocketing through the core, out the other side and back again, over and over. Each pass would release catastrophic gravitational energy, shaking the planet's structure to its foundation. The internal seismic waves would be of a magnitude never before seen, triggering global super-earthquakes and volcanic eruptions on every continent. The planet's molten core could be destabilized, potentially disrupting the magnetic field that protects us from solar radiation. In a worst-case scenario, the rhythmic internal hammering could literally tear the planet apart from the inside, fragmenting the world that took billions of years to form. This is the raw, destructive power of matter pushed beyond any sane limit. A neutron star is a universe where a fragment smaller than a coin carries the weight of a world, a reminder that some corners of the cosmos are not just strange, but inherently hostile to anything we would recognize as stable reality. The apocalyptic power of a neutron star shows how matter can be pushed to extremes, but the cosmos itself is behaving in a way that may be just as extreme. Our universe is not only expanding, it is doing so faster than our best theories predict, a discrepancy that has grown into one of modern cosmology's most significant crises, known as the Hubble tension. This is not a small margin of error. It is a stubborn, persistent gap that suggests our understanding of cosmic history may have a fundamental flaw. The problem centers on the Hubble constant, a number that describes how fast the universe is expanding today. There are two primary, highly precise ways to measure this rate. The first method looks at the nearby universe. Astronomers use pulsating stars called Cepheid variables and cataclysmic supernova as cosmic yardsticks. By measuring their intrinsic brightness and comparing it to how dim they appear from Earth, we can calculate precise distances to their host galaxies. Then, by measuring how much the light from those galaxies is stretched or redshifted by the expansion of space, we get a direct measurement of the current expansion rate. This local measurement is like using a speed gun on cars driving past you on a highway. The second method uses the ancient universe as its guide. By studying the detailed patterns in the cosmic microwave background, that baby picture of the cosmos, we can extrapolate forward using our standard model of cosmology. This model, which includes dark matter and dark energy, tells us how the expansion should have evolved over 13.8 billion years to arrive at the rate we see today. This is like calculating how fast a car should be going now based on a detailed video of its acceleration from the starting line. The crisis is this: the two numbers do not agree. The measurement from the nearby universe gives a higher expansion rate than the prediction from the early universe. The difference is about 9%, which may sound small, but given the exquisite precision of both measurements, it is a massive and statistically significant gap. This tension has persisted and even grown as our instruments have gotten better, ruling out simple observational errors. So what does this mean? It strongly suggests that something is missing from our cosmic recipe. The standard model that has worked so brilliantly for decades may need a new ingredient. Physicists are exploring several fascinating possibilities. Perhaps dark energy, the mysterious force accelerating expansion, is not constant but has evolved over time, becoming stronger in the recent cosmic past. Or maybe there are additional, exotic types of neutrinos, often called sterile neutrinos, streaming through the cosmos and subtly altering the expansion history. The most radical idea is that Einstein's theory of gravity itself, the foundation of modern cosmology, might need modification on the largest scales. Each of these possibilities points toward new physics, a discovery that would revolutionize our understanding of the fundamental forces. The Hubble tension is not a failure of science. It is a beacon, a glaring anomaly that tells us the universe still holds profound secrets about its own engine. If our most basic measurement of cosmic speed is in dispute, what other foundational truths are waiting to be rewritten? This stubborn tension in the cosmic speedometer forces us to question the very nature of reality, and one of the most unsettling answers comes from Einstein's own work. According to his theory of relativity, time itself is an illusion, our persistent feeling of a flowing present, a moving now that separates a fixed past from an open future, may be nothing more than a trick of the mind. The universe, in this radical view, does not unfold. It simply is. This concept is known as the block universe, and it reimagines reality as a static, four-dimensional sculpture. In this model, the three dimensions of space are joined by time as a fourth dimension, but with a crucial difference. In this block, every event that has ever happened or ever will happen, your birth, the fall of Rome, the death of the sun, already exist. They are fixed points or lines within this immutable structure, just as New York and Paris are fixed points in space. From this God's eye perspective outside the block, there is no special now sliding forward. The entire timeline is laid out, complete and unchanging. Our conscious experience is like a flashlight beam moving along a film strip in a dark room. We illuminate only one frame at a time, which we call the present. We remember the frames behind the beam as the past, and we cannot see the frames ahead, which we perceive as the future. But the entire film strip, from opening credits to final scene, is already there, threaded on the reel. This isn't just philosophical speculation. It emerges directly from the equations of relativity, which treat time as a dimension that can be stretched and warped by gravity and motion. If time is malleable enough that two observers can disagree on the sequence of events depending on their motion, as relativity shows, then a single, universal present cannot exist. Your now and the now of someone on a distant galaxy are not synchronized. The block universe elegantly resolves this by saying all nows are equally real, just located at different coordinates in the four-dimensional continuum. This has profound and for many deeply uncomfortable implications. It challenges our most visceral sense of free will. If the future is already out there, as real as the past, are our choices truly free, or are we just following a script written in space-time? Some philosophers and scientists argue that our experience of making decisions is genuine, even within the block. The script includes our process of deliberation. Others see it as a deterministic prison. Regardless of where you fall, the block universe forces a staggering humility. It suggests that the relentless flow of time, the feeling that slips through our fingers every second, is not a fundamental feature of the cosmos, but a biological and psychological artifact, a story our brains tell us to make sense of the world. We are not passengers on a river of time. We are patterns in an eternal, frozen landscape, mistaking our own traversal for the river's flow. If time is an illusion, then space is a lonelier place than we ever imagined. Not all worlds are blessed with a sun. Our galaxy is filled with orphan planets cast out from their stellar families to wander the eternal night alone. These are rogue planets, and their existence transforms our picture of cosmic solitude. They are not bound by gravity to any star. Instead, they drift through the interstellar darkness, untethered and invisible, following silent orbits around the galactic core. How does a world become an orphan? The process is violent and chaotic. In the turbulent youth of a star system, gravitational interactions between giant planets can be catastrophic. A close encounter can slingshot a planet out of its orbit, flinging it away from its sun's warmth forever. Alternatively, if a star system forms in a dense cluster, the gravitational pull of a passing star can pluck a planet right from its celestial cradle. The result is the same, a world set adrift. The scale of this exile is staggering. While estimates vary wildly, some astronomers suggest there could be billions, even trillions, of these nomads in the Milky Way alone, potentially outnumbering stars by a significant margin. They range from gas giants larger than Jupiter to smaller, rocky worlds perhaps not unlike a frozen Earth. For a long time, these dark wanderers were purely theoretical, ghosts in the cosmic machinery. How do you find a planet that emits no light of its own, lost in the infinite black? The answer lies in a delicate cosmic trick called gravitational microlensing. Even a rogue planet, though dark, has mass and therefore gravity. When such a planet drifts exactly between Earth and a distant background star, its gravity acts as a tiny lens, bending and focusing the star's light for a brief moment. From our vantage point, that faraway star will temporarily brighten in a specific, predictable pattern before fading back to normal. This fleeting flash is the signature of an invisible world. It is an incredibly rare and difficult observation, like watching for the shadow of a needle passing in front of a headlight 1,000 miles away, but it has been done. These detections confirm the rogues are real. The most fascinating possibility, however, is what might survive within them. A planet ejected from the warm embrace of its star does not necessarily become a dead, frozen block. A large rocky rogue with a thick insulating layer of ice or rock could retain heat from its formation and from the radioactive decay of elements in its core. This internal warmth could maintain a vast global ocean of liquid water deep beneath a frozen crust, sealed away from the cold vacuum above. In such a subsurface sea, shielded from cosmic radiation and stellar flares, the conditions for life as we know it could persist for billions of years. These dark, wandering oceans could be among the most common habitats for life in the entire galaxy. hidden in plain sight, adrift in the void. So the next time you look at the dark spaces between the stars, remember, you are not looking at emptiness. You are looking at a hidden archipelago of lost worlds, dark ships sailing on an ocean of night, each one carrying the potential for an entire secret history within its frozen heart. The dark wanderers drifting between stars carry within them the potential for entire hidden biospheres, but the chemistry of life is not confined to planets. It is being written in the vast clouds of gas that fill our galaxy, and the recipe for one of our favorite flavors is brewing right now in the chaotic heart of the Milky Way. Deep in the constellation Sagittarius, some 26,000 light-years from Earth, lies a massive, turbulent cloud of gas and dust called Sagittarius B2. This region, near our galaxy's supermassive black hole, is a stellar nursery and a cosmic chemical factory. When astronomers trained powerful radio telescopes on this cloud, they detected the unmistakable spectral signature of a complex organic molecule called ethyl formate. To a chemist, that name might not spark immediate recognition, but to your senses it is remarkably familiar. Ethyl formate is the very compound that gives rum its distinctive smell and raspberries their delicious fruity taste. This means the core of our galaxy, in a very real chemical sense, carries the aroma of a distillery and the flavor of a summer berry patch. The discovery is more than a quirky piece of trivia. It is a profound demonstration of the universe's innate creativity. Astronomers make these detections using a technique called molecular spectroscopy. Every molecule in space, whether simple or complex, vibrates and rotates at specific frequencies. When it does, it emits or absorbs very particular wavelengths of light, especially in the radio and microwave parts of the spectrum. These patterns act like a unique barcode for that molecule. By collecting the faint radio waves from a distant cloud and splitting them into a spectrum, scientists can search for those barcodes among the noise. Finding ethyl formate in Sagittarius B2 was like picking out the scent of a specific flower in a global windstorm. It tells us that the giant molecular clouds where stars and planets are born are not just simple soups of hydrogen and helium. They are rich, complex stews of organic chemistry, brimming with the precursors to life. Alongside ethyl formate, astronomers have identified molecules that form the backbones of sugars, amino acids, and even components of DNA. These are not life itself, but they are the letters of the alphabet from which life's instructions are written. The fact that these letters exist in abundance, even in the harsh, radiation-bathed environment of the galactic center, suggests that the universe is inherently predisposed to building complexity. The raw ingredients for flavor, for fragrance, and for biology are being synthesized in the darkness between the stars, long before any planet forms to host them. So the next time you savor the taste of a raspberry or catch the rich scent of rum, remember you are experiencing a flavor that is truly cosmic, a hint of the galaxy's own recipe book written in molecules scattered across the void. That cosmic recipe book is written in the chemistry of clouds, but the universe's strangest connections operate on a level far deeper than molecules. Two particles born from the same quantum event can become linked in a bond so profound it defies our intuition about space and time. This phenomenon is called quantum entanglement, and it is so bizarre that Albert Einstein himself famously derided it as spooky action at a distance. Yet, decades of meticulous experiments have proven it is a fundamental feature of reality. Here is how it works. When two particles, like photons or electrons, become entangled, they share a single, unified quantum state. Think of them not as separate objects, but as two sides of the same coin. Their properties, such as spin or polarization, are not defined individually until one of them is measured. The moment you measure the spin of the first particle and find it is, for example, up the spin of its entangled partner, no matter where it is in the universe, instantly becomes down. This correlation is instantaneous, seemingly communicating faster than the speed of light. This is what troubled Einstein. In his view of a local, classical universe, information could not travel faster than light. He believed there must be some hidden variables, some predetermined instructions the particles carried with them from the moment they were created. But a series of brilliant experiments, most famously those based on the work of physicist John Bell, have consistently shown that no such local hidden variables can explain the results. The particles truly are connected in a way that transcends the space between them. To grasp this, imagine you take two gloves, place one in a box and ship it to a distant galaxy while keeping the other here on Earth. In our everyday world, the gloves have a definite identity from the start. The one sent away is always, say, a left-handed glove, and the one here is a right-handed glove. You just do not know which is which until you open a box. That is Einstein's hidden variable idea. But quantum entanglement is stranger. In this quantum version, neither glove has a defined handedness until you open one box on Earth. The instant you see a left-handed glove, the glove in the distant galaxy becomes a right-handed glove at that exact moment. Its identity was not predetermined. It was created by your act of observation here. This instantaneous link does not allow us to send faster than light messages, a rule protected by the laws of quantum mechanics themselves. You cannot control what spin you will measure on your local particle, so you cannot use it to transmit a coded signal. However, this spooky connection is the beating heart of emerging technologies like quantum computing and quantum cryptography. In a quantum computer, entangled qubits can exist in multiple states at once, allowing them to perform vast calculations in parallel. In quantum cryptography, any attempt to eavesdrop on a message secured by entangled particles would immediately disturb their delicate state, alerting the sender and receiver to the intrusion. This means the universe, at its most fundamental level, is not a collection of separate, isolated things. It is a woven tapestry where particles can share a connection that ignores the vast distances we consider so absolute. If two specks of matter can be instantly linked across the cosmos, what does that say about the true nature of separation itself? Quantum entanglement weaves an invisible web across space, but the greatest mystery of all lies at the very origin of that web. The Big Bang, the moment our universe burst into existence, might not have been the true beginning. It could have been a transition, a phase change in a far grander and more ancient reality. To understand this, we must look at what happened in the first sliver of a second. The standard hot Big Bang model describes a universe expanding and cooling from an initial state of infinite density and temperature. But this model has a problem. It cannot explain why the universe is so remarkably uniform and flat on large scales. Regions of space now on opposite sides of the observable universe were once close enough to exchange heat and reach the same temperature, but according to the classic timeline, they were never in causal contact. It is like walking into a perfectly coordinated party where every guest is wearing the same outfit, but none of them had time to call each other beforehand. To solve this, physicists developed the theory of cosmic inflation. This idea proposes that a tiny fraction of a second after the initial singularity, the universe underwent a breathtakingly brief but exponential expansion. For perhaps a trillionth of a trillionth of a trillionth of a second, space itself expanded faster than the speed of light, inflating a subatomic speck of primordial chaos into a macroscopic, smooth and flat patch. This inflationary burst ended, dumping its immense energy into creating the hot, dense plasma of particles and radiation that then continued expanding in the more sedate hot Big Bang we usually talk about. So the Big Bang was not the beginning, but the moment inflation stopped and reheated the universe. What sparked inflation itself and what existed before it? Here, the theories become even more speculative and profound. One compelling idea is the cyclic or bouncing universe model. In this view, our universe undergoes endless cycles of expansion and contraction. Each cycle begins with a Big Bang, expands for billions of years, then eventually collapses back in a big crunch. but instead of ending in a singularity, the universe rebounds like a cosmic phoenix, and a new Big Bang heralds the next cycle. Time and space extend infinitely into the past and future with no true beginning or end. Another radical framework is eternal inflation, which leads directly to the multiverse. In this picture, the inflationary process never completely stops everywhere. Instead, it is a perpetual, bubbling sea of expanding space-time. In this frothing quantum foam, random fluctuations can cause a tiny patch of inflating space to suddenly drop out of the rapid expansion, like a bubble forming in boiling water. That bubble becomes a separate, self-contained universe with its own Big Bang and potentially its own laws of physics. Our entire cosmos is just one such bubble in an infinite, ever-growing multiverse where new universes are constantly being born. This means the ultimate origin of everything may be untraceable. There may be no first cause, only an eternal, generative process creating an infinity of realities, most of which we could never perceive or comprehend. These are not just wild guesses, they are serious attempts to answer the deepest questions left by our observations. The cosmic microwave background shows the uniformity inflation predicts, and the mathematics of string theory and quantum gravity naturally suggest these cyclical or multiverse scenarios. While we may never have direct proof of a universe before our own or of our cosmic siblings, the very fact that such ideas are scientifically considered reveals a stunning truth. The story of our universe may not have a first chapter. We may be living in a single volume on a shelf that stretches forever in a library without walls, a testament to a reality whose beginnings are as deep and endless as time itself. Our solar system is not merely drifting through the galaxy, it is traveling inside a colossal cavity, a protective shell of hot, thin gas known as the local bubble. This vast structure is roughly 1,000 light-years across, and our Sun, along with every star you can see with the naked eye, sits within its boundaries. Picture a cosmic soap bubble floating in the dense interstellar medium, its walls made of cooler, compressed gas and dust, while its interior is filled with a scorching, tenuous plasma. This is not a static relic, it is an active, evolving feature of our galactic neighborhood, and its origin story is written in stellar violence, between 10 and 20 million years ago, in the region of space that would become our local bubble. A series of massive stars reached the end of their lives. They did not die quietly. One after another, they exploded as supernova. Each cataclysm blasted its outer layers into space at incredible speeds, creating a powerful shockwave that pushed the surrounding gas and dust outward, sweeping it up like a cosmic snowplow. Over millions of years, the collective force of perhaps 15 to 20 such explosions hollowed out this immense region, evacuating most of the dense material and leaving behind this hot, low-density cavity. We are now living inside the aftermath of that ancient stellar fireworks display. The bubble's influence is more than just historical. It shapes the environment our solar system experiences as it orbits the galaxy. The interior is filled with what astronomers call the local interstellar cloud, a wisp of slightly denser gas within the greater bubble, but it is still incredibly thin by Earth standards. More importantly, the bubble's structure acts as a partial shield. Cosmic rays, those high-energy atomic nuclei from distant supernova, must penetrate the bubble's turbulent magnetic fields and walls of compressed gas to reach us. This means the flux of cosmic rays inside our local bubble is somewhat lower than it would be in the denser interstellar medium outside. It is a subtle effect, but it is a reminder that our position in the galaxy is not random. We reside in a pocket of space that was cleared and heated by the deaths of generations of giant stars. Those stellar explosions not only forged the heavy elements that make up our planet and our bodies, they also sculpted the very cavity in which our solar system now travels. The local bubble is our cosmic address, a temporary home within the Milky Way that will eventually dissipate as new star formation along its edges triggers future supernova, reshaping the galactic landscape once more. That protective bubble of ancient supernova ensures our journey is relatively calm, but other worlds endure cycles of staggering intensity. Mercury, the innermost planet, experiences a rhythm of light and dark so extreme it defies our earthly intuition. A single year on Mercury, one complete trip around the Sun, takes only 88 Earth days. Yet from sunrise to sunrise on its surface, you would wait for 176 Earth days. This means a single Mercurian day lasts 2 full Mercurian years. This bizarre calendar is the result of a precise gravitational lockstep with the Sun, a phenomenon called a 3-to-2 spin-orbit resonance. For every 2 orbits Mercury completes around the Sun, it rotates exactly 3 times on its axis. It is a cosmic dance with perfect, if strange, timing. This unusual rotation creates a world of brutal duality. Because the day is so long, one side of the planet bakes under the relentless sun for the equivalent of an Earth month, with surface temperatures soaring to nearly 800 degrees Fahrenheit, hot enough to melt lead. Meanwhile, the opposite hemisphere plunges into a deep, prolonged night that lasts just as long, where temperatures plummet to nearly 290 degrees below zero. There is no gentle dusk or dawn to moderate these extremes, only a slow, searing crawl from one inferno to another deep freeze. This also creates a unique visual spectacle for a hypothetical observer standing on the planet's surface. The Sun would appear to move across the sky at an irregular pace, sometimes slowing, stopping, and even briefly reversing its course before resuming its path toward the horizon. This is not an optical illusion, but a real effect of Mercury's elliptical orbit combined with its slow rotation. As the planet speeds up and slows down in its oval path around the Sun, its rotation cannot keep pace, making the Sun appear to wiggle in the sky. This world, so close to our star, is a testament to gravity's precise choreography, a place where a day outlasts a year and the very motion of the Sun defies expectation, reminding us that even the most basic cycles of light and dark are not universal, but are written by the unique gravitational story of each world. From the precise, scorching clockwork of Mercury to the vast, ancient bubble we call home, this journey has revealed a cosmos that is not the silent, static void we often picture. It is a living, breathing, and profoundly strange arena where the rules of our daily experience are mere suggestions. We have seen that the universe we perceive is just the glittering tip of a hidden iceberg, with dark matter and dark energy pulling the strings from the shadows. Time itself is not a universal river but a malleable fabric stretched by gravity and perhaps even flowing backwards in a mirror reality. Our most fundamental connections are written in stardust, with every atom in our bodies forged in the hearts of long-dead stars and scattered across the galaxy by titanic explosions. We are not passive observers of this cosmic drama. We are active participants, products of its most violent and creative processes, living on a world that is itself in constant, graceful motion. These 25 glimpses are not just isolated curiosities. They are pieces of a single, breathtaking portrait, one that shows a reality far more wondrous, interconnected, and humbling than we often allow ourselves to believe. The universe is not simply out there. Its story is our story, written in the warping of space-time, the drift of galaxies, and the very chemistry of life. So, which of these facts reshaped your understanding the most? Was it the backward-flowing time of a theoretical anti-universe, the lonely oceans hidden inside rogue planets, or the simple, staggering truth that you are made of star stuff? Let us know in the comments below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our exploration of space's greatest mysteries has only just begun.